right. So then, you also need a copy of this, and so do you guys. So here's one for you, and then here is one for you too. These are the lecture notes, like I said yesterday. The ones that I posted to Canvas were an older version of these notes. So some of the problems were missing. So like I said yesterday, here are the lecture notes that I should have posted to Canvas. Here was the first page that we did yesterday. So you guys can see here's the first page that we did yesterday with those definitions. But then if you go to the back side of the first page, this problem right here was not on the lecture notes that you guys had last time around, right? But this is it's an important example. I think it helps illustrate stuff a little bit more. So that's why I wanted to backtrack and go over this one as well. All right. So we're right after these three definitions. So this is, or these couple of definitions, I should say. So this is what it applies to: random experiment, sample event, probabilities, and the probability of an event. It says, suppose you flip a fair coin twice. So we're not just going to flip this fair coin once, but we're going to flip a fair coin twice. What is the sample space? So let's first jog our memories of this. What is the symbol that we use for sample space? Little s, awesome. So we want to list the sample space. So if we want to list the sample space for flipping a fair coin twice, what would be our sample space? 2 heads and 2 tails. So we could get heads, heads, or tails, tails. 2 heads or 2 tails. What else could we get? Heads, tails, or tails, heads. Right, you guys get with these being the 4 possible outcomes that we can get. Generally speaking, the most common incorrect answer that I get whenever I ask this question is that it's just heads or tails, right? But that's not correct. If you flip a fair coin twice and you need to record what you get, you're not just going to say either heads or tails, right? Because that would just be half of the story, right? You would record what you get on the first flip, which is always going to be our first letter here. And then it'll also record what you get on the second flip, which is going to be the second letter in each one of those cases. What is the probability of getting at least 1 heads? 0.75. So how did you get that? You said, well, here we know that if we're flipping a fair coin twice, then the probability of getting heads, heads, the probability of getting heads, tails, probability of getting tails, heads, and the probability of getting tails, tails. What are the probabilities of each one of these? 1/4. All of these have a probability of 1/4. Since it's a fair coin, they have an equal likelihood of occurring. So therefore, if we want to get at least 1 heads, so the probability of at least 1 heads, well, then we would get the probability of heads, heads. Here we have 2 heads. Probability of heads, tails, plus the probability of tails, heads. We obviously wouldn't include the probability of tails, tails, because there we don't have any heads. And then this is just 1/4 plus 1/4 plus 1/4, or as you correctly said, equal to 3/4, or 0.75 or 75%.
What if I asked you for sample space of like something bigger instead of just like heads and tails?
For example? Like rolling it twice?
Write this all out again?
Yeah, exactly. So if you think about it, if you're doing a 6-sided die, and you're rolling a 6-sided die twice, well then, after the first row, you can get a 1, a 2, a 3, a 4, a 5, or a 6. That's after the first row, right? But then after each one of these 6 rolls, I should say, after each one of these 6 rolls, you can also again get a 1, a 2, a 3, a 4, a 5, or a 6.
But now you're going to have one of these things at each end of this right here, because after each one you can roll it again. Does that make sense? So you're going to have 6 outcomes just for this one arm. You're going to have 6 outcomes for this second arm. You're going to have 6 outcomes after each one of these 6 arms. So how many outcomes are you going to have total? 36, right? 6 times 6 is 36. You have 6 of these initial ones. And then after each one of these initial ones, you're going to have 6 others. So you're going to have 6 here. After this one, you're going to have 12. After this one, you're going to have 18. After this one, you're going to have 24. After this one, you're going to have 30. And after this one, you're going to have 36, right? If I continue to make these branches off of all these, right? Does that make sense? So then if you rolled a fair die, then each one of those outcomes would have a probability of 1/36, right? So what happens if you would roll a 6-sided die 3 times? How many outcomes would you have? 6 cubed, or after this it would just be 6 times 36 possible outcomes, right? Does that make sense to everybody? And then just so on and so forth. Everybody good with that concept? All right, so supposing, let's go back to this one right here. If we flip a fair coin once, we have 2 possible outcomes, heads and tails. If we flip a fair coin twice, we have 4 possible outcomes, which we're already listed right here. What happens if you flip a fair coin 3 times? How many outcomes do you have? 8 or 12. I like it, that's great. It's like circling 2 answers on the bubble sheet, right? 8 or 12. What do you guys think it is? Would it be 2 cubed?
I feel like you answered a question with a question. That's not.
Well, I'm looking for an answer, so technically you guys are answering the question with the question.
Wouldn't it have to be 8 because you're only adding like another. Wait, so I guess myself. I'm just thinking 8.
You're thinking 8.
I'm thinking 8.
And why are you thinking 8?
Well, because for this one, it's just, you squared it, and then you said if you rolled it 3 times and you cube it, it's just the same concept, I guess.
It's the same concept, right? Here, in this stage right here, we did 6. We said we had 6 possible outcomes. And then for each one of these 6, we had 6 more. So for each one of the 6, we get 6 more. So that's why we said 6 times 6. And then if we went again, we said, okay, for each one of those 36, we would have 6 more. So then what we're doing is we're taking 36 times 6, or it just becomes 6 cubed, right? And then so on and so forth. Well, you're doing the same thing here. If you flip a fair coin once, you have 2 possible outcomes, heads and tails. So that's 2 possible outcomes. But then here, we're getting for each head, we're getting 2 outcomes, and for each tail, we're getting 2 outcomes. So that would be times 2. If we flipped this the third time, it would just be 2 times 2 times 2. Well, 2 times 2 times 2 is 8. And then just so on and so forth. Right? Does that make sense? So if you see something, it doesn't matter what it is, whether it's flipping a fair coin or rolling a die, or first rolling a die and then flipping a fair coin, right? You should be able to determine how many outcomes that you have, right? So let's do that. What happens if you roll a fair die, and then after that fair die, you flip a coin, right? And then that's going to lead you to some outcome, right? How many possible outcomes are you going to have there? Why would it be 12?
Because it's basically 6 times 2.
Right, exactly. So let's say that you have 12 possible doors, right? And then what you do is you're going to roll a die, and that die is going to give you the numbers 1 through 6, right? So then you're going to choose, maybe doing the opposite way around first. Maybe it makes a little bit more sense in that example. If you flip a coin first and then you roll a die, right? The outcome is going to be the same, but let's go through that thought process instead. So let's start over. Let's say you're standing in front of 12 possible doors, right? It's like one of those game shows. Which door are you going to choose? Behind one, there's like a pile of trash, and like behind the other one, there's like a trip to like, I don't know, the Bahamas, right? Which like sounds amazing. So you're like, yeah, I want the trip to the Bahamas, obviously. So then what you're going to do is you're going to flip a coin, and the coin's going to say if you land on heads, you have to pick an odd number door. And if you land on tails, You have to pick an even number, right? Makes sense? So you flip the coin, and what do you land on, heads or tails? Tails. Cool. So now you're landing on tails, so you have to have one of the even doors, right? How many doors are you left with? 6. All right. Well, then you take a die, and you roll the die, right? Then the die is going to tell you one of those 6 numbers, and that's going to be the one that you choose, right? Make sense? So therefore, if that process made sense to you, then that also means that if you roll a die and you flip a coin, you have 12 total outcomes that you're going to be able to choose from. Right? Does that make sense? All right. Everybody get the gist with figuring out how many total outcomes that you're going to have. Anybody want to do another one of those examples? It helps, and the reason why it helps is this. You can run through some scenario, and as long as you say it's a fair die and it's a fair coin, you know that all of them have an equal likelihood of occurring, so the probabilities are always going to be the same. So it could start you off with like some really complicated scenario, flipping coins and rolling die, and I don't know what else, like what hopscotch number you jump on, or something silly like that. But then you can always figure out what the probability is associated with that. Right? So everybody good with this? All right. So this is one of the examples that I definitely wanted to backtrack to. Let's see what else we left off. We did these next 2. We did this one kind of awkwardly, right, because this was the one that already gave you the answers. Then we did this stuff right here. We did this. We did the unions. Then we got to conditional probability, and that's where we stopped. So let's jump in right here for conditional probability. That's actually where we ended last class with conditional probability. So let's jog our memory a little bit again about what conditional probability is, and then we'll go on and we'll do some examples about conditional probability. All right, conditional probability. Who remembers what conditional probability is? What's different about conditional probability than what we've been doing?
The likelihood of an event happening given another event you know is already happening.
Awesome, right? So unlike just finding out the probability of A, which is the type of stuff that we've done so far, what it's now saying is, hey, what's the probability of A given that, right? And that's what this horizontal line represents again. This vertical line represents. Given that, or just given, that you know that B occurred. What was the example that we went through last class for conditional probability? Bringing an umbrella to school, right? What's the probability of bringing an umbrella to school? We said maybe it was like 2%. What's the probability of bringing an umbrella to school if it's raining outside, so you know that a B happened, and B is raining, then that would obviously have a different percentage. It might be like 20% or 50% or what have you. All right, then we said that the formula that we can use to calculate our conditional probability is finding the probability of A intersection B, which we already know how to calculate out intersections. What does it mean to have an intersection again? Exactly. It's where the A and B are overlapping, right? Wherever A and B are overlapping, that's going to be the intersection of A and B. So what we said yesterday, if you remember back to that Venn diagram looks something like this, where that shaded region was A intersection B. And then we also know how to calculate out the probability of an event. How do we calculate out the probability of an event? You what? How do you calculate out the probability of an event? No, not quite. How do you calculate out the probability of an event? So I know you guys know this. Exactly. So you're going to add up the probabilities of all of the outcomes in that event, right? So if you remember last class with that long example that we did where we had A, B, and C in it, right? Looks something like this. And over here we had like the numbers 1, 8, 9, and I think over here we had the number 2 or something like that. If I asked you to calculate out the probability of event A happening, you would have just looked up the probability of the number 1, the probability of the number 8, of 9, and of 2, and added them all together. Right? Everybody remember that? So each one of these things in here, 1, 8, 9, and 2, are called what? Outcomes. Right? So each one of these numbers in here are called outcomes. And each one of these circles is called an event. So if you're trying to find the probability of an event, you add up the probabilities of each one of the outcomes. Right, everybody good with that? So the way to calculate out the probability of an event is you add up the probabilities of all the outcomes in that event. All right. So, and then if we do this fraction right here, then we're going to end up with the conditional probability of A given B. So let's do this example. Suppose you roll a 6-sided fair die once. What is its sample space? Yep. So again, we're going to use a little s as the symbol for our sample space. The sample space has to contain all possible outcomes. Well, if you roll a 6-sided die, then all possible outcomes are just going to be the numbers 1, 2, 3, 4, 5, or 6. Then, what is the probability of rolling a 4? Whenever you see the words probability of something, what do you write down? P in parentheses. Awesome. So then the probability of, and whenever we're trying to find the probability of, we're going to stick inside of here. So therefore, this is going to become the probability of rolling the number 4. And if you roll a 6-sided fair die, what's the probability of rolling a 4? 1/6. Everybody good with all this stuff so far? What is the probability of rolling a 4 given that the number is even? What's the probability of rolling a 4 given that the number is even? 1 out of 3. Cool. So let's see how you got that, right? Let's try to do it first just by intuition, and then we'll put numbers to it and use the formulas, and we'll see that using the formulas we'll get the same numbers, our intuition. All right, so let's go through the scenario. Let's say that I'm going to roll a die up here, and I'm going to turn my back to you. I'm going to roll this die, and we're going to make it interesting. I'm going to say, hey, I'm going to roll this die, and if you get the number right, you get an A in this class, so you never need to come back. To which you say, oh, hell yeah. Right? Cool. So I'm up here, and I roll this die, and after I roll the die, right before you're about to guess, I say, no, wait. I like you guys. You guys are pretty cool. So I'm going to tell you that I just rolled an even number. To which you go, sweet. Right? Because now, are you ever going to guess the numbers 1, 3, or 5? No. Impossible. You're just not going to do it unless you absolutely love this class and you just want to hang out for 5 weeks, right? But you're probably only going to guess the numbers 2, 4, or 6, right? So therefore, if you're only going to guess the numbers 2, 4, or 6, what's the probability then that you're going to guess the number 4? 1 out of 3, right? Does that make sense? So intuition tells us then the probability of rolling the number 4, given that you know that I rolled an even number, is going to be 1 out of 3, right? Or 1/3. Does that make sense? All right. So we know that we're supposed to get something that is equal to 1 out of 3. So let's see how we can get that using this formula above. All right. So your buzzword for conditional probability is going to be the word given. Usually it's going to be given that, but if you see the word given in a problem, especially in this class, like 99% out of the time, you're going to have to do conditional probability. So we already learned 2 buzzwords last class. What were the 2 buzzwords that we learned last class? And or, right? And we do what? Intersections, and or we do unions, right? Is everybody good with that? And we do intersections, and or we do unions. All right, so now we know a third one it's given or given that. For that, we're going to do conditional probability. All right, so now that we see that we have given, and we know that we're going to do conditional probability, we can immediately write down probability of, right, again here, the probability of A given B. Well, according to our formula that we have up here, or to our definition that we have up here, we know that the probability of A given B is equal to probability of A intersection B divided by the probability of B. Right, so I'm literally just copying down the formula that we have above. Everybody good with this stuff so far? All right, so let's try to take this formula and let's try to get rid of A and B and try to substitute in the words that we have in the problem, right? We're asking for the probability of rolling a 4 given that the number is even. So if I wanted to substitute those words into this formula, what am I going to substitute in for the letter A? 4, right? Because it's a probability of rolling a 4 given that B happens, so therefore B has to be what? Even. Everybody good with this? Probability of rolling a 4 given that we roll an even number, right? Like I said, I think it might have been last class or 2 classes ago, our important first step is always going to try to take an English sentence and convert it to math symbols. If we can take this English sentence, identify how we're going to try to convert that into math symbols, those are our buzzwords. Once we can identify what we're trying to do, and we can take it from the English sentence and put it into math symbols, then we're well on our way of solving this problem. Right? Is everybody good with that? All right. So now that we know that this thing right here is the same thing as this right here, we can rewrite the rest of our formula as the probability of 4 intersection even divided by the probability of even. Everybody good with what I'm doing so far? Does this make sense? All right. So then, let's just look inside this parentheses here for a second, right? So it says the probability of 4 intersection even. But let's just look at 4 intersection even. Let's just look inside of that, right? We're looking for the intersection of 4 and the even numbers, right? The intersection, again, is where they overlap. So where does 4 intersection even? What is that? It's what they have in common. So what do they have in common? Just the number 4, right? So what we're really just doing here, if you want to have a visual for this, we have 2 things. We have the number 4, and we also have even. Well, in even, we have the numbers 2, 4, and 6. What do those 2 things have in common? Just the number 4, right? Is everybody good with that? So therefore, up here in the numerator, we're just looking for the number 4. Does that make sense? No? No good? One more time? All right. So, let's take a big step back. Is everybody good with why we're doing conditional probability? Why are we doing conditional probability? Because it says given that, right? So our buzzword says, hey, we're doing conditional probability, so we're going to use this symbol right here, right? That's our first step. Well, according to our definition, then, if we're doing conditional probability, then we're going to use this formula right here, which is why I have this copied down right here. Right? Is everybody good with that stuff? All right. Now the next thing that we want to do is we want to try to take the words in this English sentence, and we want to try to fit it into this formula. Well, the way that we read this is the probability of A given B. And then if we go up here to our sentences, it's the probability of rolling a 4 given even. So that's why we're substituting in the number 4 for A and even in for B. Right? Is everybody good with that stuff? All right. Well, now we know what A is and we know what B is. So that's why over here for this next part of this formula, for this part, I'm just substituting in 4 wherever I see an A, and I'm substituting in even wherever I see a B, so I'm ending up with this right here. Right? Is everybody good with that step? All right. Well, now if we want to go and look at the numerator, we're looking to find the probability of 4 intersection even. So what I said here was, I said, all right, let's take a step aside here, and instead of looking at the probability of 4 intersection even, let's just look at 4 intersection even for a second. And we'll worry about the probability of that here in a second. So I'm just going to take what's inside the parentheses, and I'm going to try to determine what the heck is that. Well, if we're trying to look at the intersection of two sets, we know that the intersection of two sets, just like we said up here before, is where those two things overlap. Right? That's what I said up here whenever we were going over that definition. So what we're really trying to figure out is, where does 4 overlap with evens? Well, if we're rolling a 6-sided fair die, the only even numbers that we can have is the numbers 2, 4, or 6. So what does the set of just 4 have in common with 2, 4, or 6? Well, the only thing that it has in common is the number 4. So therefore, just inside the parentheses here, 4 intersection even is just the same thing as the number 4. Right, is everybody good with that? All right, so that's the numerator. And then in the denominator, we want to have the probability of even. Everybody good with this so far? All right. Well, we already found out what the probability is of getting the number 4. We already said if it's a 6-sided fair die, then the probability of rolling the number 4 is 1/6. So therefore, the numerator is going to be equal to 1/6. Now, what's the probability of getting an even number? 0.5 or 1/2. So here we're going to have divided by 1/2 or 0.5. All right, so we have a fraction divided by another fraction. How do we simplify that? Multiply the reciprocal. So then this is going to become 1/6 times 2 over 1, which is the reciprocal of 1/2, which is just equal to 2/6 or 1/3, right? So therefore, this right here is going to be equal to 1/3. Well, lo and behold, using the formula, we got the exact same thing that our intuition told us from before. All right, is everybody good with how to apply that formula to this scenario? Anybody want to walk through it one more time? Everybody's good with it? All right, let's go on to the next example then. What is the probability of rolling an even number given that the number is 4? What's the probability of rolling an even number given that the number is 4? Would it just be 100%? All right, let's see. So you're saying, I think this should be 1 or 100%. So let's go through that scenario, right? Again, I'm up here, I turn my back to you, I'm about to roll a die. I say, hey, if you get it right, you get an A in this class, right? Now, the only thing that you need to do is guess whether I'm rolling even or odd, right? You're not guessing 1 through 6 anymore. You just have to guess whether or not I'm rolling even or odd, right? So I'm up here, I'm rolling the die. I say, hey, just guess if it's even or odd, and you get an A, and you never have to come back. And then I say, no, wait, I like you. I got a 4. Right? Are you going to guess odd? No, and if you do, you need to stay in this class for sure, right? But chances are, if that happens, we're all just like getting out of here and everybody gets an A and we're never coming back. It would be a pretty sweet scenario, right? Does that make sense of why we should be getting 100%? All right. So now let's use the formula. Let's make sure that we know how to get 100%. All right. What are we doing in this problem? What kind of probability are we looking for? Conditional probability. We know that it's conditional probability because it says given that. All right, so now we know that we're using conditional probability, and conditional probability is the probability of A given B. Well, whenever we're trying to figure out the probability of A given B, we know that we're going to look for the probability of A intersection B divided by the probability of B. Just like we did before, we're going to try to take this English sentence and use the words in this English sentence and substitute it for A and B so it'll help us figure stuff out a little bit better. Now, in this case, What is A? A is even, right? Is everybody good with even? And B is 4. Everybody good with this? All right. Well, then what we're going to have over here is a probability of even intersection 4 divided by the probability of 4. Everybody good with this? Well, even intersection 4 is what? Still just 4, right? That's exactly what we got up here. It's still just 4. So therefore, this is going to become the probability of 4 divided by the probability of 4, which doesn't matter what the probability is. It always has to be equal to 1 or 100%. Right? So technically, if you want, we can write 1/6 divided by 1/6, but it doesn't matter what those numbers are. So just be equal to 1. Unless, obviously, the probability of 4 was equal to 0. We wouldn't be able to do that. Then it would just be indeterminate, but we're never going to really see that here in this class. All right, is everybody good with how to apply this formula to those words? Everybody good with this? Any questions about this? All right, so that's conditional probability. All right, and I think everything else is similar examples, but this is definitely stuff that we haven't got to. So let's do it. All right. What we're going to see is that we're going to start doing intersections and unions and conditional probabilities. So it's really, really similar stuff to what we just got done doing. The main difference is that now our data is given to us in a table. And there's a couple of tricks that you can apply whenever you're working with tables that I want to show you. It's going to make your life a lot easier, so we're definitely going to run through one of these problems. A lot of the problems in the Past Common Final book and also on your homework are set up as a table. So this problem is going to be particularly helpful for both your tests and your homework. All right. The ELISA test is used to screen blood for HIV. Like most diagnostic tests, the test sometimes gives false positives or false negatives. Suppose a random person was chosen from the table, right? So let's take a look at this table just to wrap our heads around this table. We have this ELISA test. And in this ELISA test, the test results can either come back positive or they can come back negative. Then we also have people, and either these people can have HIV or these people do not have HIV, right? So here, if a person has, we're going to say that a person has HIV and the test result comes back positive, then we're going to say that there's 498 of those people. If a person does not have HIV, but the test comes back negative, we're going to say there's 1,990 of those people, right? So those people are like crapping their pants that they have HIV because their test result just came back positive, but they really don't have HIV, right? So it's like a false positive, right? Then here we're going to say that the ELISA test comes back negative, but a person does have HIV. There's only 2 of those people. So those people really have HIV, but the test says that they don't. And then the people who do not have HIV and the test comes back negative, that's our overwhelming majority of people. We're going to say there's 97,510 of those people, right? So then here, this row is going to have a total of 2,488. This row is going to have a total of 97,512. This column is going to have a total of 599,500 for a total of 100,000 people in our entire sample, or in our entire group. All right, is everybody good with this? All right. Then let's go on to A. What is the probability that the person who's chosen from this group at random does not have HIV? So let's first try to put it into symbols. Trying to figure out the probability of something. So here we're trying to find the probability of, or probability that person does not have HIV. What's the probability that if a person is chosen from this group at random, that this person does not have HIV? And how did you get that? Awesome. You're going to say, all right, well, in this, like, I always try to imagine, like, if you pull something out of the bag, right? Which is a little bit of a weird concept whenever you think about this scenario, because you're kind of pulling people out of the bag, but I'm going with it. Like, that's my mindset, right? So I'm pulling stuff out of the bag, right? In this bag, there are 99,500 things, here, people, which do not have HIV, right? But there's a total of 100,000 things total in this bag. So chances are really, really high that if I reach in and I pull one of these out, chances are really, really high that whatever I pull out will not have HIV. Does that make sense? So much so that 99,500 out of a total of 100,000 do not have HIV. Does this make sense? So here, if you do this, you're going to end up with 0.995 or 99.5%. And you're J. Good. Trying to learn names here, right? So J was correct, 99.5%. Everybody good with how to get 99.5%? Does this make sense? All right. What is the probability that the test is positive and the person does not have HIV? All right, what's our buzzword here? And. Whenever we're doing and, what operation are we doing? Intersection. Cool. So here our buzzword is and that is our buzzword for the intersection. So we're trying to find the probability of that the test is positive, so test positive, intersection with does not have HIV. Not have HIV. All right, is everybody good with this? All right. So whenever we're looking for the intersection, what are we looking for in the data? Where they overlap, right? That's what we're looking for. Again, whenever we're looking for intersections, the intersection between two events is where those two things overlap. So therefore here, we're looking for where positive overlaps with not having HIV. All right, if you look at the table, if I say, hey, where does positive overlap with not having HIV, it might not be super obvious. So one way to make that super obvious is this. You're looking to see where positive, this is all positive right here. Right, is everybody good that that's all positive? Overlaps with not having HIV, and here all of this stuff is not having HIV. Now it should be a lot more obvious where these two things overlap. Where does positive overlap with not having HIV? 1,990. So now let me ask you this. If I say, what's the probability of positive intersection not having HIV, would you ever tell me 1,990? No. How would you figure out the probability? Would be 1,990 people out of the total number of people. And how many people do we have? 100,000. So therefore, this is going to be equal to 0.01990 or 1.99%. Does this make sense? How to get the intersection when you're looking at a table? Any questions about this whatsoever? Everybody good? All right, what is the probability that the test is positive? What's the probability that the test is positive or the person does not have HIV? All right, what's our buzzword in this one? Or, right? So here we have or. Whenever we're doing or, what operation are we doing? The unions. All right. So here, what we're looking for is the probability that the test is positive. Union with, and that one looks like the U. not having HIV. Everybody good with the setup? All right. So if we think back to our Venn diagram for the union of event A and B, what are we looking for in the union of event A and B? Exactly. We're looking for all of this stuff, right, in both of them. So we're looking for this stuff right here. And now remember that there was a couple ways that we could do this. We could do just like Joshua said, right? Got it right? Joshua said, you could add up the probabilities of each one of the things that are in here, right? If you could imagine like this being an event, like one event, you're going to add up the probabilities of each of the outcomes in that event. Or what else could we do? We do have a formula for it? What's that formula?
So like probability of positive plus probability of does not minus B.
Awesome, right? So our formula was the probability of A plus the probability of B minus the probability of their intersection, right? You remember that was the example where we included 2 both in A and 2 in B, so we had to subtract out 2 because we counted 2 twice. You guys remember that example? So here what we're going to do then is we're going to take the probability of positive plus the probability of not having HIV minus the probability of positive intersection not having HIV, right? Let's see how we can do that if we're using a table. So first off, luckily we still have the same things that are circled. Here we have positive test, which I circled in the previous example. Not having HIV, we're going to circle this again. So, how can we calculate this out? Let's first do the way as if you would just add up all of the outcomes, the probabilities of all the outcomes, right? Just like we first started with. All right, so I want to take all of the outcomes in A, the probabilities of all the outcomes in A, plus the probabilities of all the outcomes in B. Another way of looking at that in the table is this. Here is something that is just in one of the outcomes. Here is the other thing that is in the other outcome. And here's the thing where they overlap. Right, does that make sense? So if you wanted to draw this as a Venn diagram, oh gosh, this is going to be an interesting looking Venn diagram. I need a little bit of space here, right? Because these numbers are huge. So let me do a Venn diagram up here. If we had a Venn diagram, this Venn diagram would look something like this. Where in one of the circles we have the numbers 498. That's the one that's only in positive. In one of the circles we have 97,510. That's the one that's only in does not have HIV. And where they overlap, right, this is the one that we identified in the previous problem where they overlap. This one's going to have 1,990. Right, if you want to draw it as a Venn diagram, we could draw it as a Venn diagram like this. Does that make sense? Anybody want me to go over that one more time? All right. So then, what we could do here is we could say that we could use 498 plus 1,990 plus 97,510. But again, are we just going to add up those numbers? Just like in the previous problem, did we just report 1,990? No, we still have to divide that by the total number of people that we have. Right? So therefore, here this is still going to be over 100,000. You could either write it as everything was over 100,000, or this one could be divided by 100,000, this one could be divided by 100,000, this one could be divided by 100,000. But the math still ends up being the exact same thing. Is everybody good with this so far? How do you guys feel about this? Good? Oh, hey. All right, if you do this arithmetic, what do you get? Yep, 0.99998. Right? Because technically speaking, the only people that are not included in this are what? Yeah, exactly. The two that were shown to have a negative test result, but they actually did have HIV. Everybody good with this? This is one way that we could do it. Another way that we could do it is this, right? If you go back to that formula that we did, the probability of A plus the probability of B minus the probability of A intersection B, everybody remember that formula that we did? If we wanted to apply that to this problem, what could we do? What would be the probability of being positive? Right, we'll call that one the probability of A. What's the probability of getting a positive test result? 0.24. Right, you took this number right here, and then you divided that by 100,000. Right, is everybody good with that? What's the probability of not having HIV? This one right here, right? You took this number right here, and you divided that by 100,000. So what we could do then is we could take, I'm going to write this up here, we could take 2,488 divided by 100,000. We said that this is equal to the probability of A. And we could add that then to the probability of B, and we said that the probability of B is going to be 99,500 divided by 100,000. Is everybody good with that? But now, what did we count twice? The 1,990, where they both intersect, right? This right here is the same thing as that 2 that we did in that example a couple classes ago, right? So this right here, this one we counted twice. So therefore here, we're still going to have to subtract out 1,990 divided by 100,000. Oops, 100,000. Which is just the same thing as the probability of A intersection B, which is our formula. And I guarantee you, if you do this arithmetic right here, you're going to get the same number, 0.99998. All right, how do you guys feel about those two methods coming up with 0.99998? All right, then take maybe a minute or two for yourself and see if you can do D by yourself. We haven't done one like this yet. We haven't done a conditional probability one yet, right? So let's do a conditional probability one together first. Well, how about I'll give you guys a minute or so to see if you guys can figure it out. And then we'll do it together. So if you're struggling, don't worry about it. Just give it your best shot. Does anybody need a little extra time? All right, let's do this one together. So there's two ways that we can do this one. I'm going to show you guys an easy way to do it, and then I'm going to show you one that's a little bit more tedious, but with both of them we'll end up with the exact same solution. All right, so first off here, what's our buzzword? Given that, right? I kind of gave it away, and whenever we say given that, what are we going to do? Kind of conditional probability. Awesome. So then it's going to be the probability of A given B, which is the probability of A intersection B divided by the probability of B. All right. So let's first use the formula to see how we can solve this, and then we'll learn a little bit of an easier way to do this as well. All right. Let's first substitute in the words into this problem. What am I going to substitute in for A? Test positive, right? So here this is going to be the probability of a positive test. And what B going to be equal to? Has HIV. That's going to be up in the numerator. So then down here in the denominator, we're going to have the probability of has HIV. So then if we go up here, and we did it just like we did in the previous problems, we want to find the intersection of positive and has HIV. How would you go about finding that? Where they overlap, right? So you can make a circle around positive, test result. And now we're going to make a circle around has HIV. And just like you correctly said, where they overlap, that's their intersection, right? So up here we would have 498. That's where they overlap. Is it just 498? No. Divided by the total number. Awesome. So that's just in the numerator. And then in the denominator, I'm going to try to find the probability that that person has HIV. And how do I find the probability that person has HIV? $500 divided by 100,000. Right? Is everybody good with this? I know this looks a little ugly, but does everybody get the gist of what I'm writing up here? All right, so now we have, again, a fraction divided by a fraction. So what could we do? Multiply by its reciprocal. So then it's going to become 498 divided by 500. Is everybody good with that? If I multiply its reciprocal, and then I can get rid of the 100,000s. Everybody good with what I'm doing up here? Anybody want me to write it out explicitly? All right. And then whatever this comes out to be, what does this come out to be? This comes out to be 0.996. Sounds good to me. All right. So that's using the formula. Is everybody good with how to use the formula? Let me show you guys a shortcut. Because ultimately what we ended up with was 498 over 500. But that's something that we can just pick out from the table. So here, this is the easy way to do it. Whenever we're doing conditional probability, and once again, we know that we're doing conditional probability whenever we see the word given. The easy thing to do is, whatever comes after given, so given that the person has HIV, what you can do is, you can let that become your entire world, right? And what I mean with that is this. If it says, given that the person has HIV, the only thing that you can focus on is just the information where it says that these people have HIV, right? Just this one column right here. Now if I asked you, what's the probability that you get a positive test result in this column, what would you say? 498 over 500. Are you guys good with that? A lot quicker, a lot simpler. So the trick is this. Whenever you see the word given that, you only focus on that information. So here it says, given that the person has HIV, so therefore we're only going to focus on the information for people who have HIV, which is just this column right here. If I said, hey, blah, 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 given that the test is negative, what are you going to focus on? Just the test being negative. So you're just going to focus on this line right here, right? You're not going to focus on this first line or the total line. You're just going to focus on that line right there. The 97,510 and the 97,512. You guys get the gist? So wherever you see given, that's the only thing that you focus on. All right. So, lo and behold, why don't you guys try to do E by yourself? Does anybody need a little extra time? All right. So what is the probability that a person has HIV given that the test is positive? First off, what test are we going to do here? What are we trying to figure out? Conditional probability. We know that it's conditional probability because, again, we have the word given. So we're trying to find the probability of A given B. Then, what's going to become our entire world? Just tests being positive, right? So we're only going to focus on this row right here. Then if we're just focusing on that row, what's the probability that the person has HIV?
20%.
Yeah, how'd you get that?
I just took 498 over 2488.
Everybody good with 498 over 2488?
So if you have HIV and you take this test, there's a 20% possibility that it will be positive.
So this comes out to, what did you say, 20 something?
That's 0.200 or 0.20.
Cool. So let's see. So what is the probability that the person has HIV given that the test comes back positive? No, so what's that saying? It's saying that if you only focus on the people whose test came back positive, then of those people, 20% of them are going to have AIDS, right? Which seems like a low percentage. But if you think about it like this, what would be worse? You telling somebody, hey, you might have HIV, let's do some more tests. Or would it be worse to say, hey, somebody has HIV and you're like, no, you're good. Right? What would be worse then? telling the person who has HIV that they're good, right? Like, yeah, no, you're fine. Like, go about your business, right? Like, that would be worse. So you would want to err on the side of caution. And if there's even a faint possibility that you could have HIV, well, let's do another test, right? And that's what this right here is saying. We're gonna set our threshold for additional tests at being really, really, really low. That makes sense? Cool. Everybody good with E? All right, then see if you can do F by yourself. Anybody need a little extra time? All right. What kind of probability are we going to try to calculate out here? Again, conditional probability because we're dealing with given. Right, so we're looking for the probability of A given B. We have given that the person does not have HIV, so therefore we're only going to focus on the person does not have HIV, right? Just on that information. So we're only going to look at this information right here. Person does not have HIV. All right, if we're looking at just the information for a person does not have HIV, what is the probability that the test comes back positive? How'd you get that?
1990 over 195,000.
Cool. So we're going to have 1990 divided by 99,500. And this comes out to, you said, about 2%? Seems right. Everybody good with 1,900 divided by 99,500? All right, then let's do the last one together. What's the probability that a person does not have HIV, again, given that the test is positive? What are we only going to focus on? Test being positive. So we're only focusing on this. And then what is the probability that the person does not have HIV? What are we going to do? Awesome. We're going to have 1,990 divided by 2,488. And this looks like it's, what, like 87? 799. All right, how do you guys feel about finding conditional probabilities? How do you guys, it's a lot easier than using the formula, right? Yeah, so a lot of times if you, especially if you're working with a table, like we were doing up here, if you know that little trick, it makes these types of problems a lot easier. Everybody good also with finding the union of two events and the intersection of two events using a table? Right. Let's go on to the last page. And that is for independent events. So I believe that the formula for independent events is included on your formula sheet. So here it says that if events A and B are independent, then that means that the probability of A intersection B or what they have in common, is equal to the probability of A times the probability of B. So therefore, if they are not independent, then what do we know is true? Then they don't equal, right? And then they're dependent. Awesome. So we know that if they're not independent, then this is just the same thing as them being dependent. But if they're not independent, well, if they are independent, then these two things are equal. So therefore, if they're dependent, then we know that these two things are not equal. So then we have the probability of A intersection B does not equal the probability of A times the probability of B. So basically, if you have a question and it says, hey, are these two things independent? What are you going to do? You're going to calculate out the left-hand side, you're going to calculate out the right-hand side, and if the left-hand side is equal to the right-hand side, then they're independent. And if the left-hand side is not equal to the right-hand side, then they're dependent, or they're not independent. All right, is everybody good with this? All right. So, let's do it. A single fair die is rolled once. Let event A be 3 and event B be 1, 3, and 5. Are A and B independent? What are we going to do? Cool. So we're trying to figure out if they're independent. So that's kind of like our buzzword to what we're doing. So we're going to try to figure out A intersection B. We're going to try to figure out the probability of A, and we're going to multiply that to the probability of B, and then we're going to see whether or not these two things are equal. So I'm going to put a question mark over that equal sign because that's what we're trying to determine. Right? I don't want to say that they're equal yet because that's what we're trying to figure out. If the left-hand side is equal to the right-hand side, then they're independent, and again, if they're not, then they're not independent, or they're dependent. All right, so let's start off with the left-hand side. What is in the intersection of A and B? 3. So then therefore I can rewrite this right here as the number 3. Is everybody good with that? Then if this is a fair die, what's the probability of rolling the number 3? So therefore we have that the left-hand side is equal to 1/6. Now we need to figure out the right-hand side. All right, what is the probability of A? Well, the probability of A is, again, what is in A? Only the number 3, so this is just the same thing as the number 3. So then, this is just going to be the same thing as 1/6. What's the probability of B? Good, so that's the same thing as the probability of 1 plus the probability, right? I'm going to put parentheses around this, plus the probability of 3 plus the probability of 5, which I think everybody will agree then the probability of rolling an odd number on a fair die is just 1/2. So you guys tell me, is the left-hand side the same thing as the right-hand side? No. So this is not equal. And therefore, because it's not equal, is it dependent or independent? Everybody good with how to determine if two things are independent or dependent? All right, before we finish up here, let's go over the concept. So this is just the mechanics behind figuring out if two things are independent or dependent. But let's try to get like the intuition, the overall concept of what it means for two things to be independent. First off, as it says right down here, this is extremely important, that independent is not necessarily the same thing as mutually exclusive. So let's try to see what the difference is between independence and mutual exclusivity. Mutual exclusivity, we said, was what? What does it mean for two things to be mutually exclusive? Nothing in common, right? That they absolutely have nothing in common whatsoever, right? So mutual exclusivity might be something like if it's raining outside and well, that's not a good example because it can be raining and sunny at the same time, right? If it's snowing and 90 degrees outside in Charlotte at the same time. that's pretty much impossible, right? Like that's a safe one. So those two things would be mutually exclusive. If it's snowing outside and if it's 90 degrees outside at the same time. Not going to happen at the same time, right? Independent is different. Independent is saying, does one thing influence something else from happening, right? So an example would be me wearing black socks and me having a biscuit for breakfast, right? This morning I had a biscuit for breakfast, but me eating a biscuit for breakfast had nothing to do with whether or not I was going to put on black socks, right? One thing did not influence the other, right? So therefore, eating a biscuit and putting on black socks are independent events, right? Does that make sense? But they definitely are not mutually exclusive because this morning I both put on black socks and I also ate a biscuit for breakfast. So both those two things can happen at the same time, right? So therefore, that's an example of where the two things can happen at the same time, but one doesn't influence the other, which is mutually exclusive versus independent. Is everybody good with the concept of the difference between those two things? So therefore, for mutually exclusive events, we just saw that their intersection was empty. But for independent events, we have to do some calculations to see if the left-hand side was equal to the right. Is everybody good both behind the mechanics of those two things and also the overarching concept of the differences? All right, and that's where we'll wrap it up today. Obviously, we still have a couple of minutes in class, so I'll hang around for a couple of minutes if you want to come up and ask.